Welcome to episode 6 of the Euler project. This is a series in which we use Clojure to solve the problems in the online Euler project and then take them to the max. Problem 6 is a lovely little problem that asks us to calculate the sum of the squares and then the square of the sum of a set of consecutive natural numbers. The problem asks us to find the sum of the squares of the first 100 numbers and subtract from it the square of the sum of the first 100 numbers. Now, honestly, when I first saw this problem, my first impression was that it was going to be too simple to be worthy of an episode. I mean, here, just watch how easy it was to solve. All right, well, I think we can just solve this in the REPL. So let's just start up a REPL here. And we're going to need the first 100 natural numbers. So define N100 to be the range from 1 to 101, because it doesn't include the last one. It's an open interval. Okay, and what did I do wrong? Oh, heavens. Oh, yes. That's not a defined function, it's a define, so let's just get rid of that n there. Okay, all right. And now the first of n100 is going to be a 1, and the last of n100 is going to be a 100, if I can type that properly. There's going to be 100, yep, okay, good. All right. So now we want a square function, right? So let's define a function square, which takes n and is the product of n and n. Good, and we can test that. Square 3, good, is a 9. Fine. Okay. So now we want the sum of the squares. So define sum of squares to be the reduce plus, that's how you get the sum, of a map square of n100. Good, and that should be some number of 338350. Okay, fine. Now what we want is the square of the sum. So define square of the sum to be the square of the reduce plus n100. And the square sum is some very large number. Okay. And now we want the difference between the square sum and the sum of the squares. And that is 251,64150, which is the correct number. This had me a little concerned at first because, well, how do I make an episode out of something so simple? I mean, I didn't even have to write an actual program to solve it, but then I started to play around a little bit. The first thing I did was just write the program anyway. I mean, why not? It's simple enough. And you can see it right down here. This is the final program, and it reads pretty well, right? I mean, we take the sum of the squares of the natural numbers and the square of the sum of the natural numbers, and we create the difference, and, well, let's just try it. Here, let's just run a REPL. And, okay, now we say E6 of 100, and that should give us the number we expected. And you'll notice I put an n on the end of that, and that's just because of this right here, because I want to play with larger numbers, right? But that's the right answer. So here, let's do this, E6 of 1,000. Okay, that's interesting, isn't it? Let's try 10,000. Okay. Now, do you see a pattern forming there? I mean, they all begin with 2, 5, and then after 0 to n zeros, there's a 1, and then uh, 1 or more 6s, followed by a 4, and then a 1 followed by a bunch of 6s and a 5. And that, although it's not a perfect pattern, it's close. Here, let's do this. There, that should give us a nice list. Yeah. There. Took a little while, but the pattern holds. Isn't that interesting? I mean, look at that. It's 25 and then 0 star, regular expression, 0 star. So 25, 0 star, 1, 6 star, 4, 1, 6 star, 5, 0 star. Now, why? Why indeed? I mean, the difference between the sum of the squares and the square of the sum of the first n natural numbers, where n is a power of 10, appears to match this regular expression. Now, maybe we shouldn't be too surprised that a positional regular expression expressed in base 10 matches a base 10 number generated by powers of 10. Right? Maybe that shouldn't be too surprising. On the other hand, that's a pretty weird regular expression, isn't it? And I think it probably deserves a little bit of thought. Do you remember way back in episode 1 of this series when I told you the story of Gauss as a young boy who had been given the math problem of summing up the first 100 integers, and he came up with a clever little formula to do it? And that formula was n times n plus 1 over 2, or 1/2 n squared plus 1/2 n. Now, if you think about it for a while, you're going to realize that that formula will always generate a nice pattern, something that could be matched by a regular expression for any power of 10. Because if n is a power of 10, then n begins with a 1 followed by a bunch of zeros. And if you square that, it's still a power of 10, and so it's a 1 followed by a bunch more zeros. And then if you take half of a power of 10, you get a 5 followed by a bunch of zeros. So if you add n squared and n together and divide by 2, you're going to get a 5 followed by a bunch of zeros and a 5 followed by a bunch of zeros. So the sum up to 10 is 55, and the sum up to 100 is 50/50, and the sum up to 1,000 is 500/500, and of course all of those results would match this lovely regular expression, 50 star, 50 star. So now if the formula for the sum of the squares of the integers also has a similar kind of formula, it seems likely that that's going to match some kind of regular expression, doesn't it? And that would just kind of solve the whole issue. Now we would know why the difference matches a regular expression. So how can we derive the formula for the sum of the squares of the integers? Well, first, let's see if I can show you how to derive Gauss's formula for the sum of the first n integers. And we'll use a little calculus to do this because that would be fun. Now, here's the line f of x equals x, right? Just a nice linear equation. And what we want to do is sum up the areas of all these rectangles, which are the integers from 0 up to n. Now that's going to be roughly the area under that line, which of course is this integral, right? this definite integral from 0 to n of f of x dx, and of course that's 1/2 n squared. But that gives us the area under the triangle. Now we got a problem, because the area under the triangle does not include this last integer here. So we have to add n to this. But that's too much because we've got to subtract all these little triangles here. And if you look at these little triangles, they have a base of 1 and a height of 1, and so their area is all 1/2, and there are n of them. So we're going to subtract half of n from n, and we're going to get the standard formula, which is 1/2 n squared plus 1/2 n. By the way, you can verify this by just looking at this triangle itself, which has a base of n and a height of n, so that's 1/2 n squared, and then of course you do the same kind of thing with the extra rectangle and subtract off all those little triangles. So it all works out pretty well, doesn't it? Can we use a similar strategy to derive the sum of the squares? Let's try. Okay, so we'll just start with the same kind of drawing, right? But this time the function that we're going to take the area of is going to be x squared. So f of x is x squared. And of course, the definite integral of f equals x squared is 1/3 n cubed, right? Okay, everybody knows that. Well, that is the area under this parabola up to n, but does not include the last little rectangle, so we've got to add a full n. But then we have to subtract out all these little parabolic sections here, of which there are n, and I'm going to let all you calculus whizzes work that out because that's well beyond my abilities to calculate. But the answer is the sum of all the squares up to n is n times n plus 1 times 2n plus 1 divided by 6. Or, I like this even better, it's 1/3 n cubed, which is the integral of x squared, and it's 1/2 n squared, which is the integral of n, plus n over 6. Anyway, we can just plug these formulas into our program, and that ought to improve things by quite a bit. Okay, so here's the old program, which did the repetitive adding, and that, of course, is slow. And then here's the new program, which uses these simple formula here that we just derived, and it ought to go a lot faster. So let's just see that. I'm going to time, let's see, E6 of 1,000,000. Now that should take a little bit of time. Not too much. Took 375 milliseconds, a third of a second. Okay, fine. Let's just repeat that to make sure that that number remains relatively constant. Yeah, okay, you can see it goes from about 0.4 to 0.3, somewhere in there. Now let's do the time of E6-2, which is our faster one, of 1,000,000. And I think I need to put the n on the end of that one. Let's see. Yep, there we go. Ooh, 200 microseconds. And by the way, 200 microseconds, they're at 0.08, yeah, 89 microseconds. You can see that's going to be kind of variable because the resolution of the clock really isn't that good. I suppose I could have done it like a bazillion times or something. But here, let's do this. Let's do the time of E6 of 10,000,000. And that's going to take it, well, what? 4.8 seconds. 4.8 seconds. So, yeah, that's a long time. And we can do the same thing with E6-2. And I think I need the n on the end of that. And that's going to take us, 73 microseconds. So of course, this is going to go much faster. That's not a big surprise. I wonder how big we can go, like E6-2 of 1,000,000,000,000. That's 1,000,000,000,000, right? Okay, let's see what that gives us. Oh my goodness. Oh yes, I forgot the n. Yeah. And okay. Oh my goodness, that was fast. And look, it still matches our regular expression, which of course we now understand, don't we? Those two formula when applied to a power of 10, create regular patterns in the digit stream, and you subtract those regular patterns and you still wind up with a regular pattern. So it's not at all surprising that we can match this with the regular expression, although it's still kind of fun, isn't it? I'm awfully intrigued by just how simple these programs are. I mean, look at the sheer elegance of this code, how simple, how beautiful it is. I mean, even the slow one.
Write it in C and see how simple and elegant it is.
Write it in C? Write it in C? Yes, I'll write it in C. Okay, so I wrote it in C. I mean, why not? Now, ignore everything else for the moment and look right here. That's the algorithm, right? It looks a little different than the Clojure program, but if you look at it carefully, you'll see exactly what's going on. We're going to loop for I equal 1 to n, right? And we're going to add I to the sum of n, and we're going to add I squared to the sum of n squared, so that calculates our two numbers. Then we're going to square the sum of n so that we've got the square of the sum. And then we're going to subtract the square of the sum from the sum of the squares. No, the other way around. We're going to subtract the sum of the squares from the sum of the square of the sum. There we go. Got it. And then we're going to print that. Maybe not quite as simple and elegant as the Clojure program, but clearly not terrible. Now then there's this stuff here, and that's just setting up the memory because we need, large numbers here. We can't just use integers for this. We have to use big integers. And of course, C does not have a big integer library, at least not one that I wanted to use. And so I wrote my own, and I'm going to hold the big integers in large character arrays, which need to be zeroed out. And then, of course, we have to have the add to function, don't we? And we need to have the square function, and we need to have the subtract from function, and we need to have the print num function. None of those are standard. And so as we back up the chain here, you see here's the square function, which takes a big integer, which is just an array of characters, or, the way C works, a pointer to a char array. Anyway, we have a temporary product, which we zero out, and then we move the number coming in, n, into the product, and we multiply that by itself, and we move that back to the number, so it squares the number. Okay, fine. How do you do a subtraction? And here we've got two big integers, right? Two big integers coming in, destination and n. So it's going to subtract n from destination, leaving it in destination. How do you do that? Well, okay, you just loop through and you subtract each digit from the destination. So that's pretty simple. And then you have to deal with the borrows. Well, the borrows are pretty simple. Every time you find a digit that's negative, you simply increase the next digit. Or you decrease the next digit, you borrow from the next digit and add 10 to that digit, and you just keep doing that until you've got something positive in that number. That's how you do a subtract. Now, doing an add is something similar to that, although when I did my add, I was not adding two big integers, I was adding a long to a big integer because there was no need to do anything more than that, although the algorithm is roughly similar. And you can see what's going on here. Here's the addition. I need to take the long n and break it out by digits, so that's what the remainder here does, and the quotient there does. And here's the carry logic here, right? So if it's more than 10, then we subtract 10 and add 1 to the next digit over. Works the same way. The real interesting one here, I'm not going to talk about these up here because they're kind of obvious. You can look at the code if you want to. But the really interesting one is the multiply function, which, if you study this for a little while, doesn't take very long, you will realize that that's just the long multiply algorithm that you were taught in 3rd grade. With the partial products and everything. If you remember that algorithm, you will look at this and say, yep, that's just regular old long multiplication. Anyway, I will leave you to look at this code if you want to, just as an exercise in in self-immolation while writing some C code. Does it work? Well, I believe it does. Let's see. Of a million. I wonder it'll probably do that pretty well. Yeah, there we go. All right, took a little while. Not maybe as well. Maybe as long as that Clojure program. That looked like about 1/3 of a second. I'm not going to do the timing. I wonder if it'll work for 10 million. 1002, 1003, 1004, 1000. Oh, see, just about as long as the Clojure program. Isn't that interesting? You may have noticed that there weren't any unit tests in that C program. Did I violate the discipline of test-driven development when I wrote it? Well, yes, in the sense that I didn't write any unit tests, but no, in the sense that I still followed the test-driven development cycle. You see, this is a really simple program. It was easy for me to code a little bit and then run a little bit, and I could use some strategically placed print statements to make sure that everything was functioning properly. So had you watched me, you would have seen the test-driven development cycle, that iterative short cycle, definitely being used. It's just that I didn't write any unit tests. Now, do I feel dirty about that? No, I don't feel dirty about that. This was a one-off program. It's never going to be used again. It's never going to plague anyone else. So, no, I thought it was a perfectly acceptable approach to test it live in tiny little increments without writing a bunch of unit tests. So what's the takeaway from this episode? Well, I can think of a few. Number one, even really simple problems can have some interesting little investigations to dig into, don't they? And I was also kind of surprised that the runtime of the C program was roughly equivalent to the runtime of the Clojure program. I had not expected that, but well, you can't argue with the numbers. I suppose you could critique the efficiency of my C algorithm was maybe not, at its maximum. And then the other thing that I thought was interesting was that the expressiveness of Clojure, if it's well structured, is pretty good, but then again, the expressiveness of the C program, if you ignored all the things we had to do to make it work, was also pretty good. So those are kind of my takeaways. And anyway, I hope you learned something. I hope you had fun. I hope you enjoyed yourself. You're not going to want to miss the next exciting episode of Euler, Euler 7. And what deep mysteries will we find there?